So we are going to start a new chapter now. This one is nuclear physics. Nuclear physics is actually a very good chapter to go through in A2 in the sense that it's actually pretty easy and the marks that are normally allocated are very generous. Okay, it doesn't require much to understand nuclear physics and to do their questions. All right. So before we go into the calculations part of it, we just go through some introduction. Now, in your AS last time, when you were doing your questions on particle physics and you were required to calculate out the mass of your nucleus, you may have encountered a case where you needed to use some value called the unified atomic mass U. Okay, the unified atomic mass U is obtained from your data sheet on the second page of your data sheet. The value is 1.66 times 10 power minus 27. The unified atomic mass by itself is actually just defined as 1/12 the mass of a single atom of carbon-12. All right. Now you are really just supposed to know how to get the value from your data sheet. What is the definition of unified atomic mass is not really required. All right. Now, why do you need to use unified atomic mass here in this chapter is because when you're talking about nuclear physics, you are often dealing with atomic particles. So when it comes to the masses of the atomic particles, you using the kilogram is actually an inconvenient unit to use because the values in kg would be really, really small. Okay, for example, if I tell you the mass of a particular nucleus is maybe 5.6 times 10 power minus 29 kg, notice this one is really, really small. So in order to make it somewhat more convenient to deal with, you will sometimes express the mass of an atomic particle in terms of U instead. So if let's just say you have the mass in terms of kg, and then you want to express it in terms of U, all you just really need to do is just that you divide it by the value of U. So in my case, if I wanted to find the mass in terms of U, it will be 5.6 times 10 power minus 20, was it 29? Okay, minus 29. Divide by the value of one atomic mass unit is 1.66 times 10 power minus 27. You will eventually get the answer as some value. Just let me calculate it out. It will be 0.338 U. Okay. Now you compare looking at the masses in this form versus this form. Looking at it in this form seems to be more convenient. That's what they say. All right. So if you look at the table below, this table here lists down certain common atomic particles as well as their associated masses in terms of U. All right. Now, for this particular chapter, especially, when you do your calculations involving the masses, you are supposed to maintain the number of SF during your workings. You see, for the masses of the atomic particles that are listed here, notice that they are not your usual 2 or 3 SF. They are actually listed to at least 6 SF and above. So there's a reason for that. Because your nuclear reactions usually involve very subtle changes in masses, very, very small changes in mass, the difference is really, really small. So because the difference is really, really small, you need to work to a higher number of SF in order to be able to detect them. That's why here you'll notice that your masses are all in a large number of SF here. So subsequently, when you do your calculations in your exam, please make sure that you maintain the same SF. Okay, don't round it up. You only round it up in your final answer. But before that, during your calculations, do not round it up at all. Okay. Yeah, and also another thing that I probably should mention to you. Remember last time in your AS, when it was mentioned to you to find the mass of a nucleus, you will actually take the nucleon number multiplied by U, right? So that time I mentioned to you that the U is actually the average, in bracket, average mass of a nucleon, where in your case, a nucleon could either be a proton or a neutron, isn't it? Proton or neutron. All right. Now, there's a reason why we say that last time in AS physics, but now in A2 physics, we don't no longer say that the mass of a proton and neutron is just 1 U. Okay. You look at the table values for neutron and proton, notice that the masses are actually quite different if you look at it in larger number of SF. You see, neutron is 1.008665, proton is 1.007276. Now, there clearly is a difference here between the masses, but if you were to look at just say 3 SF, this one would be 1.01 at 3 SF. This one will also be 1.01 at 3 SF. Okay, that's why here in your AS physics previously, we just mentioned to you, if you are talking about the masses of neutron and proton, just take it as 1U. Okay, because up to 3 SF, the values are actually the same. Okay, but if you're talking about larger number of SF where you require higher accuracy, higher precision, you would need to consider up to maybe 7 SF or so in order to be able to detect the differences. Okay, just so you know. All right. Now, then after that, we go to the concept of missing mass and binding energy. All right, so we go to the concept of missing mass and binding energy. Okay, this one, I will make use of a reference particle. We make use of alpha particle since it's a more common particle we always deal with. Now, if I talk to you about an alpha particle, you will say that the nuclide notation is alpha 42, okay? And it consists of 2 protons and 2 neutrons, okay? It has 2 protons and 2 neutrons. So these are the constituent particles that make up your alpha particle. So you imagine this, you have 2 neutron, 2 proton. You're supposed to combine them together to get an alpha particle. Alpha particle, you know, is actually your helium nucleus. Okay, so the constituent of your helium nucleus or alpha particle here consists of 2 protons and 2 neutrons. So you have to combine these individual neutrons and protons together into the small volume of your nucleus. So it probably now looks like this, where you have 2 neutrons and then you have, say, 2 protons too. Okay, so but the thing now is that when people try to look at the masses of the constituent particles and the mass of the nucleus itself, they notice something strange. You see, if in my case, I try to compare the total mass of the nucleons, maybe I just write that at the top. If I try to compare the total mass of the nucleons right over here versus the mass of the nucleus itself, by right, you would assume that the masses should be equal because it's conservation of mass. But the thing is that when people try to actually find out the masses between the nucleons and the nucleus itself, they actually found out that it's not the same. Instead, what they found out was that the mass of your nucleus itself is actually less than the total mass of the nucleons. So somehow or another, when you go from here to here, you have mass loss. Okay, so you suddenly have mass loss here. There's a difference in mass. Okay, there's a difference in mass here. All right, so this nucleus is actually lighter. These nucleons, the total nucleons, is actually heavier. Okay, there's suddenly a mass loss here. All right, now why is there in the first place a mass loss? Why is there a difference in the mass in the first place? Now, bearing in mind that the difference in mass is actually very large in terms of atomic particles, because if let's just say you talk about an alpha particle, the difference in masses for the alpha particle is actually 0.030377 U, which is equivalent to the mass of 55 electrons. So from an atomic particle point of view, it's actually a very large mass, worth 55 electrons. Okay, so why is this happening in the first place? Now, it comes from the fact that when you want to combine your nucleons together, you actually have to do work. Okay, Now, if you recall what you learned in nuclear physics before this, we always told you that proton is positively charged, isn't it? So protons by themselves are always positively charged. If you try to bring the protons close to each other, there's always going to be a strong repulsion between them. So if let's just say these are your two protons inside your nucleus right now, they are actually always trying to repel each other because they are both positively charged. So there's actually a strong repulsion. And the closer you bring the protons together, the stronger your repulsion. But somehow you're able to somehow squeeze them together into the small volume of a nucleus. So this kind of implies to you, you had to do work to bring the neutrons and proton particles together. Okay, there is repulsion between them, but if you want to squash them together into the small volume of your nucleus, you must do work here. Okay, so your strong nuclear force here is actually doing the work to bring the neutron and proton particles together. All right, so in your case, the work done means that you must have energy to do so, right? Okay, so in your case, where did the energy to do the work actually come from? The energy to do this work actually came from the direct conversion of mass to energy, all right? Which will explain to you why your nucleus is lighter than your individual nucleons. So what is actually happening here is that when you go from nucleons to your nucleus, you have to do work. You need energy for that, but there's no other energy around for you to use. So the only way you can actually get that energy to do your work is by converting it from mass. So in your case, your nucleons here, it lost a bit of its masses. Okay, some mass is lost and converted to energy. So that energy, or rather that mass, is converted to energy to do work to combine your nucleons together into a nucleus. Okay, so in your current case here, we actually do not say mass is conserved, nor energy is conserved. If you say that mass is conserved, it is wrong. If you say that energy is conserved here, it is also wrong. We cannot say it's mass conserved because you can clearly see that the masses before and after are actually not the same. Okay, and likewise, you cannot say that energy is conserved here because you needed energy to do the work to combine the nucleons together. This energy did not come from other forms of energy. Instead, it came from something else. It came from mass. All right. So rather than saying energy is conserved or mass is conserved, we instead use something else. We use a different term. Instead, we say that mass energy is conserved. Okay. Now, it's because of this reason why here you see in your AS physics, last time when we tell you for any nuclear reaction, what are the quantities conserved? We say it's proton number, nucleon number, momentum, and mass energy, right? But we do not say mass is conserved or energy is conserved individually. All right. So that is just one thing to note. Okay, so your nucleons go into your nucleus. You convert mass into energy so that you can do work to squish them together inside a nucleus. So once you squish them together inside a nucleus, the nucleons together into a nucleus, the particles will be stuck there. If let's just say you want to break them apart into their nucleons, you want to break the nucleus apart into the individual nucleons, you are looking at doing something opposite like this. Let me just try and draw it out using a different color. You're trying to do it in the opposite direction like this, right? So if let's say you have a nucleus and then you want to break it apart into the individual nucleons, you actually have to supply energy equal to what you spend to combine the nucleons in the first place. You have to give back the same amount of energy in order to break the nucleus apart. So in your case, once you supply the energy which is equal to whatever work you did in order to bring nucleons together in the first place, the nucleus will break apart into the individual nucleons. That energy that you supply will be converted back into matter, or in other words, mass. So going from left to right here, what will happen is that you suddenly have mass gain. Okay, your mass has increased. You will suddenly have mass gain here. All right. Your energy that you put in has gone back into your masses. All right, so you restore back the masses that you lost in the first place. Okay, now that energy that you supply in order to break your nucleus into the individual nucleons has a very specific name for it. That one is called binding energy. Okay, binding energy is a definition that will come up quite often in your exam questions. So binding energy is defined as the energy needed to separate a nucleus into individual nucleons completely to infinity. Okay, completely to infinity, this one is the keyword here, all right? And then also just now notice that when I mentioned that between the nucleons and the nucleus, there's usually a difference in mass. Either it's mass loss or mass gain. That mass difference is called your mass defect, okay? It is the difference between the mass of your nucleus and the total mass of the separate nucleons when the nucleons are separated to infinity. Okay, these are two terms that you would really need to remember to be able to answer your exam question later on. Okay, now, so we know that when you combine nucleons into a nucleus, it involves energy, it involves work done, it involves mass changes. If you want to calculate that energy that is associated with the mass change, you would use a very particular equation that was actually found by Einstein, that was actually proposed by Einstein. If you wanted to calculate the energy involved due to mass changes, there's a very specific equation you would use. That one is E equals to delta mc squared, where E is the energy that you got from the mass, delta M is the mass change that your reaction has experienced, and then C is your speed of light squared. Okay, C is your speed of light, but then after that you need to square it. Okay, so in general, this equation E is equals to delta mc squared. It can be used to find two things. The first one is that this equation itself can be used to find binding energy when breaking a nucleus into its individual nucleons, and also to find energy released during nuclear reactions. Okay, E equals to delta mc squared can be used for two specific cases. To find binding energy when breaking a nucleus into individual nucleons, this is the first case, and also to find energy released during a nuclear reaction. Okay, it's not just specific for finding binding energy, it's also to find energy released during a nuclear reaction. You will see that later on. Okay, then after that, because I mentioned to you that there's two different situations where you would use that equation, the delta M here that you will use from this equation actually depends on the two cases. It differs according to the two cases. If say you're using E equals to delta mc squared to find binding energy, the delta M here is supposed to be the mass difference between the nucleus and the total nucleons, okay? But if you are using it to find the energy release during a nuclear reaction, your delta M here is actually the mass difference between the reactants and products inside the reaction, okay? So that's just one thing that you guys need to be aware of, all right? So a lot of times you will notice that when you go and do your questions, they tend to use mass and energy terms interchangeably, where they tell you that 1U, a mass difference of 1U is actually equivalent to this amount of energy, 931.3 mega eV. So in case you haven't learned what mega eV is already, mega eV is actually 10 power 6 eV. And this one 931.3 mega eV. The big M here is actually mega. Okay, this one is mega, is 10 power 6. It's the prefix of the unit eV. You would have learned eV in AS, in particle physics. I think I taught that in AS physics last time. Now, eV is actually just another unit of energy, where we say 1 electron volt is actually worth 1.6 times 10 power minus 19 joules. Okay, it's another unit of energy, just as we say U is another unit of mass. Okay, so that one, just bear that in mind. Right, then after that, the next part I need to go through with you. Okay, now you know that binding energy was the energy required to separate a nucleus into individual nucleons completely to infinity. So why do we need to know binding energy in the first place? All right, because binding energy is actually a measure of stability. Now you consider this. When your nucleus is formed from separate nucleons, I mentioned that energy is converted from mass. To pull the nucleus apart, work must be done against the forces holding the nucleus together. Hence, energy known as binding energy must be supplied in the first place. Now, if in the first place you need more energy to split a nucleus, that means it is actually much more stable. Okay? If it's like something, if the nucleus requires less energy to split apart, that means it's actually not stable in the first place. But if you need more energy, more effort in order to break it apart, that means it's actually stable. Okay, so binding energy here is actually a measure of stability. All right, but be careful about binding energy. Binding energy is not energy stored in your nucleus. It is just simply the energy that must be put into the nucleus to pull it apart. Okay, it doesn't tell you anything about the energy contained by the nucleus. It is just telling you how much energy you need to break the nucleus only. Okay, so binding energy, just now I told you binding energy is a measure of stability, but specifically binding energy per nucleon is a better measure of the stability of the nucleus. Okay, this is the standard that they use to compare the stability of the nucleus. Not just binding energy, but rather binding energy per nucleon. Okay, so here we will say that the bigger the binding energy per nucleon of a particular nucleus, the more stable the nucleus is. Okay, so from there, there's a particular graph that you need to remember, because some of your questions for this chapter requires you to remember the shape of this graph. Okay, now if you were to plot a graph of, say, binding energy per nucleon versus nucleon number for a number of different elements, generally you will get a graph shape that looks like this. Okay, maybe it's better if I just draw it out in general for you. You tend to get a graph shape that looks like this. Okay, wait, just give me a moment. You tend to get a graph shape that looks like this. Just disregard the sharp peaks there in the first place, right? If you were to plot a graph of binding energy per nucleon versus nucleon number, this is generally the graph shape that you get. Okay, this is PE per nucleon. This is nucleon number. Okay, it looks like that in general. Okay, now from there, there's one particular point that you will always be interested in, the peak. You will always be interested in the peak of that curve, which is, say, right over here. Okay, so at this point here, you will notice that because you have the highest BE per nucleon, this is actually the most stable element, the most stable nucleus. Okay, because it has the highest BE per nucleon. So it's actually the most stable element. Okay, why did I write most element? It's supposed to be most stable. Okay, it is the most stable element here. All right, and this usually belongs to a specific element, ferrum 56. Okay, it belongs to ferrum 56. Okay, so always remember that curve and what is the value for the peak. Okay, what's the nucleon number for the peak? Is usually 56, because ferrum 56 is actually the most stable nucleus. Okay, now from here, if let's just say next time they ask you to go and plot out the positions of certain nucleus given their nucleon number, because you already know this curve and where 56 is, you will be able to guess where are the relative positions of the nuclei. Let's just say if I ask you to plot out uranium 235, 235 is your nucleon number. So you know this one is 56, 235 must be towards the right side. It will probably be somewhere around here, because nucleon number 235 is here. Okay, then let's just say if they give you some other random element, I do not know what element is that. Maybe I just say it's X 43. So 43 would be on the left hand side of your graph. So it will be somewhere around here. Let me use a different color. It will probably be around here. This one is 43. This is element X, some unknown element X. Okay, so that's the reason why you need to know this graph and what is the nuclear number for the peak. Okay, it's so that you can identify the positions of other nuclei. All right. Okay. Then after that, another thing that you would need to know here is this one. Notice that in your graph, there are certain sharp points here. There are certain specific peaks here, like this. Okay, so what we'll just mention to you is that those peaks actually belong to certain specific elements like helium, carbon, and oxygen. Now, these elements have a higher binding energy than usual because the atomic configuration is unusually stable. That explains to you why you have those sharp peaks there. Okay, the sharp peaks there indicate a higher than usual binding energy per nucleon, which means a higher stability than usual. That is usually for these three elements. Okay, these three elements are usually more stable because they have an unusually stable atomic configuration. Okay, now in your exams, we will never ask you the origins of the peaks. We won't really bother about asking the peaks. What are the elements that the peaks belong to? Why are there even peaks in the first place? No, the exam questions will never ask you that. Okay, so this is just some other additional knowledge. All right, now apart from allowing you to determine what are the positions of certain nuclei given the nuclear number, this curve here, this graph here, allows you to determine what particular nuclear process will actually occur, whether a fission or fusion process will occur. Okay, now fission and fusion, you may have learned it in IGCSE already, so this is kind of like a revisit of that two terms. Now, if you look at the next page, when it comes to nuclear fission, fission occurs when an unstable heavy nucleus absorbs a neutron and then splits into two daughter nuclei of about equal masses and more neutrons to become more stable. Okay, so this is something large breaking apart into something smaller. Okay, that is typically what fission reaction is. Fusion is the direct opposite of that. Fusion is where two light unstable nuclei join together to form a heavier, more stable nucleus. This is where two small things join together to become something big. Okay, so this is what fission and fusion actually is. Now, how does it relate to your binding energy curve here? So to be able to determine whether something is going to undergo fission or fusion, let me just give you some example. If let's just say, for example, I have some element here. Okay, maybe I better just draw it here. Let's just say, for example, I have an element here whose nuclear number is 200. Okay, now if I want this nucleus to become more stable, there's two ways in which the nucleus can go about. Either it goes downwards. You see, if my nucleus with nuclear number 200 wants to become more stable by undergoing a nuclear reaction, there are two directions you can consider, either going downwards or either going upwards. Okay, I need to use a different color for this, maybe green. It can either go upwards or downwards along the curve. But you notice one thing, if you go down the curve, your BE per nucleon is actually decreasing in value. So this is actually becoming less stable. This is actually becoming less stable, which is not you want. Okay. Yeah, before I go any further, this one is something I probably should mention. The goal of any nuclear reaction is to become more stable. Okay, whenever you have any kind of nuclear reaction, the goal of that nuclear reaction is always to become more stable. Okay, you will never have a nuclear reaction occurring naturally to become unstable. it will always try to become more stable. That's just the way things are. Okay, so in your case, if you have a nucleus with nuclear number 200, it undergoes a nuclear reaction. It by right does not want to become less stable. It therefore will not go down the curve. Okay, but if you go up the curve like this one, notice that your nuclear number, notice that your binding energy per nucleon is actually increasing. So this is actually becoming more stable. Okay, so you're becoming more stable by going up the curve. This is what your nucleus would do. Now notice what happens if you go up the curve. If you are starting from 200 and you start to go up the curve, your nucleon number will start to decrease. Okay, from 200 you go down to some lower value. Now how are you going to be able to have a decrease in nucleon number? To be able to have a decrease in nucleon number, this is achieved by your nucleus breaking apart. Okay, therefore it's going to be fission. All right, if your nucleus goes up the curve over here, it is going to be fission because your nuclear number is decreasing. When your nuclear number is decreasing, it already implies to you you must be breaking apart. Okay, so you are having fission here. All right, now a similar reasoning can also be applied on the left hand side of 56, at the left hand side of nuclear number 56 here. Let's just say, for example, you now have some unknown element here at some random nuclear number value. Maybe let's just say I give you 5 here lah. Okay, just for example's sake. So here, same thing as before, you can either go up the curve like this, or you can either go down the curve like this. Okay, so going up the curve, you are actually having an increase in binding energy per nucleon. So this is actually becoming more stable. Whereas for the part where you go down the curve, your binding energy per nucleon is actually decreasing. So you're actually becoming less stable. So which one would your nucleus, which path will your nucleus take? It will actually try to become more stable. So it will go up. It will not go down. So now in the process of your nucleus going up, notice what happens to your nucleon number. If you're going up the curve, your nucleon number is increasing. Okay, so that means your nucleus is combining together with something else. So this one, you can actually think of it as, since your nucleon number is increasing, you're combining together with something else. Therefore, it's going to be fusion. That's why here we will say that going up here is going to be fusion. Okay, that's just the gist of it for this binding energy per nucleon curve.